In the earlier videos, we've focused on functions of a single variable. So the function f has a single argument or input, and it gives us back the value that it maps to. However, if you recall, a function just is something that maps one set to another. So it could be that rather than starting with a set x, we look at pairs of things in x. We use a notation x squared to represent ordered pairs like x1, x2. An alternative notation for this would be the cross product, x times x. So these are all the pairs, x1, x2, such that x1 is an element of x, and x2 is also an element of x. In general, you could take some set x and some set y, and write the cross product to mean all pairs, x and y, where x is an element of capital X, and little y is an element of capital Y. Since we're using the times notation, it's convenient to write this as capital X squared. Now, if we have a function that takes ordered pairs from x and maps it to elements of y, so you can think of this as pairs of numbers mapped to a number, if x and y are both the real numbers, then we would write f of x1, x2 to denote the value that the pair x1, x2 is mapped to. Well, you could do the same thing for three arguments. You could take f of x1, x2, x3. For instance, f might be your utility function that tells you how happy you are when you consume x1 numbers of apples, x2 numbers of bananas, and x3 number of oranges. And you can keep going. You can have as many arguments to a function as you want. In general, f of x1, x2, all the way through xn is the value that these n numbers are mapped to. One of the nice things about functions of a single variable, so f of x, is that we can graph that. We could put on the vertical axis f of x, and the horizontal axis we can mark x. But what do you do if you have, let's say, two variables? You're going to need 3 dimensions to be able to graph it. So you're going to put x1 on this axis, you're going to put x2 on this axis, and then on the vertical axis you can mark f of x1, x2. So perhaps it looks something like this. That's always going to be difficult to draw. What if you had 3 variables? Well, you're going to need 4 dimensions, and as you know, we can't draw things in 4 dimensions. Now, even when we draw a 3D picture, it's very hard to tell what's going on. A more convenient way to visualize a function of 2 variables, rather than drawing its graph, is to use something like a topographical map. If you were to go to, let's say, Google Maps or Apple Maps or whatever, you can often choose the topography, and it gives you these things that look something like this. It gives you the height here, the height of the ground here, the altitude of the ground here, and so forth. You pick a point, and then you draw a curve through all the other points that are at the same altitude. We could do the same thing for a graph. Pick a point x1, x2, and draw a curve through all the other points that map to the same value y. So for instance, this point x1 prime, x2 prime might map to the same value as x1, x2. And you can keep doing this, and maybe you find all these different points. What you do is you just draw a curve through that. This is what we call an isolevel set of f at x1, x2. So if you drew all of the isolevel sets, you might get something like this. If you move along one of these curves, all the points map to the same value according to f. That's how we're going to visualize functions of 2 variables. Another thing we were able to do with function of a single variable was write down its derivative. But how do you write down derivatives of functions of 2 variables? That's where we're going to use the concept of a partial derivative. A partial derivative, with respect to, let's say, the first argument, is where we hold all the other arguments fixed and we treat them as constants, take the derivative with respect to the first argument. Similarly, you can find the partial derivative with respect to the second argument, and the third, and the 18th, however many variables there are. So let's stick with a 2-variable function, and we want to find the partial derivative of f with respect to x1. We're going to treat x2 as a constant. Obviously, this is going to mean the partial derivative with respect to x1 is not going to be the same as the partial derivative with respect to x2, because when we take the partial derivative with respect to x2, we're going to treat x1 as a constant. The notation we use for a partial derivative is the small Greek letter delta. If you recall, for the derivative, we used the letter d, but for a partial derivative, we're going to use the Greek letter delta. So delta f, delta x1, is the partial derivative of f with respect to x1, its first argument. Let's do an example. Suppose we want to find the partial derivative of this function, x1 squared plus x2 squared plus 2x1 x2, with respect to x1. So we're just going to take the derivative of this, where x2 is like it were a constant. So we're going to apply the addition rule here. The derivative of x1 squared with respect to x1 is just 2x1. That's what we have here. When x2 is a constant, x2 squared is a constant as well. So the derivative of x2 squared is 0. Finally, the derivative of 2x1 x2, the function is the constant 2x2 times x1. So if we take the derivative, it's just the constant part. So it's 2x2. So then we have the following partial derivative of f with respect to x1 is just 2x1 plus 2x2.